Okay, I also start recording the class from now. And to mute. Okay, and Sun, please mute your microphone. Otherwise, I have an echo. Yeah, that's good, Carolina. You can set up some variables. Okay, so Kai Wen John, that looks good, except line 15. It's usually not a good idea to use degrees in when dealing with angles in any kind of program, because the standard libraries for math in any programming language actually expect angles in radians. So one convention that has proven to be very useful for myself and my students and lots of other programmers is to always use radians when dealing with degrees, and only to convert them to degrees when you print them out or save to a log file or something like that. Yeah, I think that's better. Okay, let me start from the top again. Okay, very big. And it's import matplotlib.pyplot as PLT, not matplotlib. And we have a straggler. TTT bear still needs to register. Yeah, so you can use calculate then the extent of the hockey stick in the x direction. That's also correct. So let me So now if you are still stuck, then you can watch my screen. I'm going to go through a little bit how I would set up this particular problem. First of all, we want to throw these hockey sticks, and I have to make some computation on it. So it will probably be a good idea to just collect them in some sort of collection. So in Python, the standard data structure for generating collections is our list. So we'll take a list. But now the question is, what exactly do I want to store in the list? And I guess there would be three numbers, X and Y location of the stick, where I would take that to be the center of the stick. And then the angle theta that the stick has with the either horizontal or vertical up to you. If you, whichever one you prefer. So what I want is sticks is equal to, and then since those don't actually change, I'll make them tuple. So that will be x1, y1, theta 1, x2, y2, theta 2 for the second stick, so on and so forth. So n is the number of sticks. So, and until I know my program works, I set it small so I don't need to wait so long. Then I need to generate a stick that is thrown. I need to actually throw the stick. And there I need another couple of variables. The track width, in this case, is 1. The number of tracks. In my picture, how many did I draw? 1, 2, 3, 4. The stick length is a constant. Also 1. And I think those are all the variables that I need. And I make it a function. Stick length. And the standard imports for Matplotlib would be like Matplotlib pyplot in order to get the plotting module, and import that as PLT, and import NumPy as MP. Anytime you want to plot something using Matplotlib, this is the most common import statements that you want to do. I also need math and random, so we can import those libraries as well. And then, okay, let's set up our variables here. So the X location is rand range. What does that actually do? So we'll pick one. We'll pick a random number between 0 and what did I call it? Track width times number of tracks.
Professor?
Yeah.
May I ask what's the difference between random.uniform and the random.rand range?
Rand range gives you a random element out of a range, so it's totally different.
Oh, okay. It is different
It gives you
from
like
the
yeah, if you
argument.
have you have range 2, 12, 4, right? Then that would give you 2, 6, 10, and then 14, but that's not included. So it'll give you a random number that's either, so this is range, and then rand range. Oh, how come I have so many of these now? Okay, rand range would give you 2, 6, or 10, one of those three numbers. But it won't give you a random number between 2 and 12.
Okay, I see.
Yeah.
Thank you.
So it is used in a different kind of scenario. How long do I make the track? Oh, yeah, make it square. So that's why I dropped the hockey stick. And then theta is uniformly distributed between 0 and 2 pi. 0 and 360 degrees. So then the stick is x, y, and theta. And the sticks, I append that stick. You can do that all in one single statement if you want to. I just break it down into smaller things. And then we can return the sticks. And then that's it. So I can call throw sticks, 5 of them with the default arguments. And I get then the output here. So one lands at 2.98, 3.55, 1.35 in radians, 2.02, so on and so forth. Right. So now we have the sticks. Now, just for fun, let's just draw them. So if I want to draw the stick, then I need to draw one. Would that be? Yeah. Actually, I don't really need the stick length here, right? I could leave that argument out because when I create the sticks, I just take the calculate center positions. When I draw them, I need to know the stick length. But yeah, I don't like that very much either, but okay. So we throw the sticks on the track. Set the labels. You should get used to that. If you write a scientific paper or your thesis, then every graph should be labeled all the time. So it's best to put these 3 onto every graph that you draw, even if you don't think you're ever going to need it for your scientific publication. Who knows whether you will need it in the future or not. Then I want to draw the sticks. So I could do this for S stick in sticks, right? That will iterate through all the sticks and give me an individual stick. I can do it slightly faster, or then what I would do is X, Y, theta is equal to stick to get the individual components, or I can write it like that too. So now I want to draw the stick. Frame. And you'll see later on why I record this. So plot command takes mainly two arguments, the set of x coordinates and the set of y coordinates for the line that I want to draw. So,
Professor, sorry.
Yeah.
There is an echo, and I don't know if someone is with mic mute.
No, looks like all the mics are turned off except mine and yours now.
Yeah, I don't know.
So we have x and y coordinates that we want to draw, and yeah, okay. So what would I have to draw? X plus stick length divided by 2, x minus stick length divided by 2, multiplied by cosine theta. So this depends now on how you orient the angle. If 0 degrees is straight up, then this should be sine. If 0 degrees is to the right, like mathematical, then it should be cosine here. That should be plus. And then this would be y. Where now I have to use the sine instead of the cosine. Then I can say I want to plot them with a continuous line in red and the line width, make it big because it's a stick, so let it 7. And artist equal to that. Okay, that may work. No, unknown variable. Sticks is not defined. Oh. So now I have 5 sticks that I threw onto the tracks here. This is not quite so nice, right? Because I didn't draw the track. So you can now either continue in your own programming, or if you got stuck, then you can copy this code, my code, and actually draw the outline of the tracks, like these rectangles here, the black rectangles. Otherwise, let's see how far you got. I'll take a break then.
Hey, Professor.
Yeah.
Yeah, why is that the stick you draw, the length of each stick is not the same?
That would be because I didn't set the aspect ratio.
Oh, got it. Thank you.
If I, that's true, that makes it look a little bit weird. So you want to set, for this kind of drawing, you want to set your aspect to be equal. And then it should look better. Yeah. And what? Oh, okay. I just draw the rectangle. So and then we have track width and number of tracks. Track width equals 1. Number of tracks equals 4. And now I have to draw a frame is equal to this. So this would be I times track width I plus 1 times track width. Then we go up. So we go I plus 1 track width. Then we go back I. Then we go down to the origin I. So in order to draw that rectangle, I need to draw 5 points. 1, 2, 3, 4, 5. And then for y, that would be 0, then 0, then track width times number of tracks. Track width times number of tracks and 0. And then I don't actually know what the marker is for black. I think it's K maybe. And line width 2. Draw tracks. Yeah, so now it looks like I have the tracks there. And K actually is the correct marker for a black line. If I want to draw a black line here. and then let's have some fun. You don't actually need to follow along now. This is more interesting for the projects, for the programs that we're going to write later on in the course. Because now, instead of just drawing the picture of throwing the sticks, we'll actually do a little animation, a little video, actually animate a little video of the sticks falling. So in this case, I need to include the animation module. But I always forget how to do that. No error. Okay, small mistake. Also, plt.close here. And so my interval a little bit too slow, but yes, it should be not 10,500 is probably enough. So now you can see the individual hockey sticks appearing. So that is the main part of the program. Actually, all the drawing is not really necessary. The only thing you need to do now is for your, once you have your sticks, you need to check how many of those sticks cross the line, right? And then you're actually done.
It's about 60% of sticks cross the line.
60%, that's actually correct, but for 100, that is actually correct. But let me try and figure out what that number actually is. It is not a 60% one. It just happens to, how would it change if the length of the stick changes?
I think that the stick, the length of stick doesn't matter.
No, it does. The smaller the stick, the less chance that it's going to cross the line.
Oh, let me check.
Yeah. The interesting thing is that this probability actually is related to pi. So you can use this procedure in order to estimate pi, like 2 pi r, that pi. Which makes this the first application of probability in order to sort of measure geometrical properties, in particular the value of the constant pi. Actually, I can...
Yeah, Professor?
Yeah?
According my simulation, I find it won't change with the stick width. Yeah, and
Did you change anything else? It definitely changes with the stick width, right? Because if the stick is, let's say, 10 centimeters instead of 1 meter, the probability that it crosses is much lower than if it's 1 meter in length.
Oh, but I thought the roll width is shortened along with the stick width.
No, of course, if you change, what is important is the ratio between the length of the rail and the length of the stick. If you change both and you keep the same ratio, then your numbers are not going to change. But if you change only one of them, that's what I meant, right? If you only change one of them, then the probability is going to change. But it depends on the ratio. But you're also right. I mean, it's a good observation that you made that whether it's 1 centimeter and 1 centimeter long stick and 1 centimeter long rail, or 1 meter long stick and 1 meter long rail, that doesn't matter. Or 2 meter long rail, 2 meter long stick, then the probability will not change.
Okay.
Yeah. So let's implement a routine that actually checks if a stick is crossing the line or not, crossing the boundary or not. So we have a stick and we have the number of tracks and the track width. Right, track width, number of tracks, yeah. So then I can get the positions. Now, in order to determine whether we crossed the track or not, the y coordinate doesn't matter, right? In fact, for running the simulation, it would have been okay to simply just ignore all the y coordinates and set them all to 0. Then the probability won't change, right? Because the y coordinate is just going to move the sticks up and down, but it has no impact on whether the stick is going to cross the lane boundary or not. But since we want to draw it, I included the y coordinate. But now when I need to check if we crossed a track or not, then of course I can I can ignore the y coordinate. I just use the x coordinate. So the stick is going to start from x minus math cos of theta, and it's going to x plus math cos multiplied by the stick length. So now how do I check if that crosses the thing? That would be x. So the lane would be the lane number for the left part of the stick would be this divided by the track width. And the second one, the end point, and now I think I just have to check if the integer part of lane 1 and lane 2 is not the same. So if the floor of lane 1 is not equal to the floor of lane 2, then crossed is true, else crossed is false, and we return crossed. I think that's right. Yeah. So now let's change our drawing. Oh, no, I don't need this. If lane crossed stick
Pardon?
yeah.
Professor, can you explain the physical meaning of the parameter lane 1 and lane 2?
Oh, that's just the, that would just be the number on the lane. Lane 0, 1, 2, 3.
Oh.
So I'm just checking if the lane that I'm in, if it's not the same, that means I must have crossed the boundary, right?
Yeah. Okay, I see.
Yeah. So that was
Thank
just
you.
the cheap. There's other ways to do that. This was just the easiest, cheapest way I could think of checking whether it crosses a lane boundary or not. Instead of calculating whether for each one of the lane boundaries, if it's on the right side and on the left side, or on the left side and on the right side. That would have been more work, I think. So if that one is true, then the color is, we'll plot it in red, and else color is blue. Oh, and I didn't want to. Lane crossed, crosses line. Okay, crosses line. And here I didn't want, should be any two.
Professor,
Mm-hmm.
what are you doing now? Like to be head and was head red and blue? No.
Yeah, now I'm just coloring them in. So if they cross the line, I draw them in red. Otherwise, I draw them in blue.
Okay. Oh, another thing that I saw, like you one stick, they are out of the boundaries.
That's
Like,
okay. I just assume that the lanes keep going on forever.
Okay, but I could like change the random when I am generating the sticks. I could like just change and set a different number to not cross the boundaries, right?
Yeah, you could do that too. Yes, I don't think that will change the result. That would be possible. So now you can see they're red if they cross the line, and here we have one that doesn't cross the line. So if I now want to throw 100 sticks, then I can do that. Where do I create the sticks? Throw sticks. Let's throw 50 sticks. Okay, so that looks good. So now the question is, what does this actually signify? And the interesting thing is that this allows us to estimate the probability of pi. Sorry, not the probability, the value of pi. Pi doesn't have a probability. The reason for that is because if you think about it, for any given angle theta, of the stick, the probability of crossing a line is, in my case, it would be cos theta, because that's think about the line and the stick having the same distance, the same width, like in the puzzle, in the original problem statement. Both of them were 1 meter. Then for 0 degrees, it's clear then the stick is horizontal, so it must cross, right? There's no possibility that it does not cross any line. And if it's 90 degrees, then it's guaranteed not to cross any line. So the probability that we will cross a line is sort of, we have cosine theta, distance that we can move, and 1 minus cos theta, probability that we're not crossing the line. But now if they are not the same length, so if the lane is twice as big, then that probability would be halved, right? Because the projection here for this stick, that projection is going to be the same length, but the lane is going to be bigger. So then the probability that we cross is going to be less, or if the stick becomes smaller. So that probability would be, in my case, multiplied by the lane, by the stick length, divided by the lane width. And 1 minus that. For not crossing a boundary. So for 0 degrees it's 1, but then it depends. If the stick is the same length as the lane, then this here would be 1. Then the cosine of that would be, cosine theta would be 1, so there's 100% probability that we cross if we throw the stick at 0 degrees. And if we throw it at 90 degrees, then there will be 0% probability. If the stick length is half as long as the lane width, then there's only a 50% chance that we will cross any lane. So now that we have to integrate. If you think about it, now we have to integrate the probability for theta from 0 to 2 pi. Where's my pi letter?
Professor, are you sharing your screen or not anymore?
It just crashed, so it's just coming
Oh,
back
okay.
online now. Pi. So the probability of crossing from integrating over 0 to 2 pi of cosine would be negative sine pi. Yeah. And so that means the probability would be 2 times the track, 2 times the stick length divided by d lane width multiplied by pi. So now I can simply count that probability, right, by dropping 1,000 sticks. Then I know what the probability is. So that would be the number of crosses divided by the total number of sticks that I throw. That has to be equal to this. And then I can reformulate it and solve for pi. So that would be and this should be lane width multiplied by pi. So multiply by pi, and here we need to multiply by n over s. And then let's So now we have, so that probability, if the stick length and the lane width is exactly the same, then n divided by s would be the estimate, 2n divided by s would be the estimate for pi. So if we throw 100 sticks and we have 64 that cross, then 100 divided by 64 is 1.562, which would be a estimate of pi over 2. So I multiply by 2 to get an estimate of pi. So let's see. Just make sure the equations, yes. If I increase the lane width, then the value of, if this stays the same, then the value of pi would go down. If I increase the stick length and it stays the same, then the value of pi will go up. Yeah. So then I just need to write one more function. Stick length, and what arguments did I pass to the crosses line? Oh, it says track width, number of tracks. Okay. So S is 0 for X for stick in sticks if, what is it, crosses line, stick length, track width, number of tracks, S is equal to S plus 1, and then I could return S divided by the length of the sticks, and that would be the probability. Then let's just plot that. But I don't want to do an animation now. It works if you run it on your own machine, but on Google Collaboratory, if you make an animation longer than a minute, then it will be very slow. So for I in one, 2, let's say 5,000 and 500 steps. Then ys is mp zeros, length xs. For x in xs, sticks is equal to create throw sticks. So we throw that many sticks. Track width equals 1. Stick length is equal to 1. Number of, what do I call that? Number of tracks. Track width. Track width. Number of tracks is 4. Stick length is 1, so we want to throw the sticks, that many. Track width, number of tracks. P is equal to here I need to know the index as well as the actual value. So Python provides a convenience function enumerate here, which gives you both the index. So that's what you would get for I in range length xs, as well as the value x at the same time. That makes it a little bit faster to write this. Otherwise I have to write it in 2 lines. Or actually, yeah, I'll just write it. If you don't know about enumerate, it's also no problem. You can write it like this. For I in range length of the xs, x is equal to xsi. And then these are the sticks. Then P is calc the probability of the sticks, stick length, track width, and number of tracks. So the estimate now for pi would be 2 times stick length divided by the lane width divided by divided by p. 2 times stick length divided by track width and then here this is n over s, but I want what I get from my calc probability function is S over n. So I need to divide it by p rather than multiply it by p. And here I didn't call this lane width, I called it track width. Now the other thing that's interesting to notice here is that this equation is completely independent of the number of tracks that we actually have. Right? And that sort of makes sense because I could just remap all of this to track 0 and nothing would actually change as far as the probability is concerned. Right? So how many tracks I have on my running track when I run this experiment doesn't really matter. Right? It's not in the equation at all here. The only reason why I need that is so that I can actually draw it. By p, y's of I is equal to p, is equal to the estimate. And then let's plot this. Plt dot figure x is fig dot add subplot. Ax dot set aspect. We'll set the aspect equal. Set title to estimate of pi. X label is number of sticks that we throw. Y label is our estimate of pi. Now it's equals to 3. And then I also want to plot 0 to does that work? 0 to xs minus 1, the last entry in xs. And this would be math.pi math.pi k dash dash, which gives us a dashed line. Let's see. For n. Yes, okay, so that must be an integer here. So I'll just cast it to an integer. 5. Let's see what's wrong there. Okay. And figure 2 or figure 3 is figure 3, 0, 0 figure. So Count Buffon figured this out already in the 18th century, 1777. I think pretty impressive for its time. And the very first time that we used probability theory, randomness, in order to measure geographical values, in particular the value of pi here. Take 3 is only. Oh. Oh. So if I throw a stick, then that's 0, so I cannot divide by p. Oh, it's equal, so that's a mistake. In this case, I don't want to have equal because it ranges up to 5,000 and the other one ranges up to 3. And here you can see our estimate of pi. So even if we're just past, let's say here, that's about 50, right? Then our estimate of pi keeps getting better and better. Past 2000, then we're already getting pretty close to the real value of pi, which is the black dashed line here. So I think that's pretty neat. Very nice usage of probability theory in trying to solve a geometrical problem. Or, of course, at that time, people already knew the value of pi. They had calculated it using other methods, but it's an interesting way of getting the value, estimating it. It's also the first use of this kind of simulation, Monte Carlo simulation, in order to extract the value. So you can sort of see how the error decreases for the estimate of pi, and the more you run this, the closer you will approach the real value of pi. So it is sort of an asymptotic approximation to the true value of pi. One interesting story about this is that in the 1920s, it's actually the first time, even though 1777 Count Buffon proposed this procedure, nobody actually had the patience to throw thousands of sticks onto a racetrack. So it took until 1920, and then some mathematician actually did it, and he threw 150 needles or something like that. But nowadays, people are actually convinced that the guy was cheating because his value came out to be much too close to the true value of pi. It was correct to within three 10,000s or something like that. So they said he was probably cheating a little bit when he did all the throwing. Okay, good. So that's it for BBC puzzle for today, and also allows you to learn a couple new things, hopefully, for Python and Matplotlib programming, in particular the way that we can plot important and visualize important features of our simulation that will turn out to be very important later on in the course, because it's hard to visualize these things just in your mind. It's easier if you can plot a chart, and that sort of shows you what the probabilities are doing. Because in a sense, robotics is a difficult domain to work with compared to other software engineering domains. For example, operating system research, if you do something wrong, then often you get a kernel panic, right? You get a segmentation fault or something like that. Or a trap because you didn't pass the right parameters to or you don't have permissions to access the admin space. So your program crashes dramatically. Whereas in robotics, we're really just getting floating point numbers, position of the joint, position of the ball in the image. So there's thousands and thousands of floating point numbers that you can print out, but whether they're correct or not, you really cannot tell by just reading 3.29, 3.31, 3.75. Right? Often you need to be able to plot it, visualize it, in order to get a feeling for whether your algorithm, your controller, is actually doing the right thing. If you implement the controller, then the controller is just going to send joint coordinates to your elbow. But whether these are the right joint coordinates to pick up the water bottle or not, or whether the error is somewhere else, that the vision system doesn't recognize the position of the water bottle correctly, is impossible to do without having some powerful visualization tools at hand. And Matplotlib is quite amazing in what it can do, I think. Of course, MATLAB is also good, but it's not free. So but otherwise, yeah, you could use, I think Matplotlib is sort of the same as MATLAB. There's some more features in MATLAB for very specific applications, I guess. It would make sense. But for our course, it's sufficient to use the Matplotlib and be able to use the tools correctly. Okay, good. So then let's take a 5-minute break, and then I want to continue with the introduction to probability theory. Okay, so 5-minute break. So we're back. There's other ways you can do this test, by the way, too. You don't need a running track, clearly. Like a tiled floor is supposedly what Count Buffon wanted to use when he came up with this procedure. Let's run it longer, up to 50,000, just out of interest's sake. Okay, good. Then we'll continue today with the introduction to probability theory. And let me share that slide. Set or a Jupyter notebook. Okay. So probability theory, the axioms were derived by Kolmogorov in 1933. They state that the probability of some proposition A being true, that's denoted as PR of A, and if we have a set of events, then the probability of an event occurring must be greater than or equal to 0, and the sum of all the probabilities for all possible outcomes, they have to add up to 1. And then probability of A or B is the probability of A plus the probability of B if A and B are mutually exclusive. That's all that is necessary. From those 4 statements, 4 axioms, you can actually derive all of probability theory, including the chi-squared test and tests for t-tests, and all of that can be derived from these 4 axioms. So we can draw it as a Venn diagram. Yeah.
Professor, we cannot see your slide.
Oh, okay. Yeah, sure. Yeah.
Oh, yeah. Better. Thank you.
So the probability of A or B is the probability of A plus the probability of B, but then we will have counted the intersection twice. So that would be, we have to subtract the probability of A and B one time from that sum. Then we can have discrete random variables. So x is a random variable, and it's a discrete random variable if it can take on a discrete set of values. Now, rolling a dice, for example, would be an example of a discrete random variable, because it can only return the values 1, 2, 3, 4, 5, or 6. You can never roll a 5.5 with a dice, right? Or drawing cards. If you draw 5 cards and then your random variable is the number of hearts that you have drawn, then that can only take on discrete values. No heart, 1 heart, 2 heart, 3 heart, 4 heart, 5 hearts. That's it, right? No 4.5 hearts that you can draw. So that's indicated as the probability of x having the value xi, or just probability of xi. And p is called the probability mass function in this case. So examples of discrete random variables would be tossing a coin, right? That would number of heads, number of tails is a discrete value, not a continuous random variable. So one of the interesting things that we can do is, how do we simulate an unfair dice? So a dice usually is considered to be fair. You want to play with a fair dice, otherwise people are going to steal your money if you go to the casino, because they know which number is more likely to come up. But a fair dice, each face has a 1/6 probability of showing up. So rolling a 1 has a probability of 1 out of 6, or 1/6, and rolling a 2 is 1/6, so on and so forth. Then the sum of all the events will add up to 1. And now, how could we simulate an unfair dice? So a dice where the probabilities add up to 1, but maybe the probability of rolling a 3 is 50% instead of 1/6, which would be 0.16, wouldn't it? Okay. Yeah, so it'd be 0.166. So for fair dice, I have the following outcomes. I can roll a 1, which has a probability of 1/6. I can roll a 2 with a probability of 1/6. I can roll a 3, 1/6, and so on and so forth for the other one. So if I roll this dice, then I get an indication here. Just one of the values that I can roll from that dice. I pick one of them, and then I return the result, what I rolled, and the index that I chose for this particular function. And then I can should be so we set the dice to be a fair dice at the beginning. And if I roll it 1,000, if I roll it how often? 10,000 times, I get 1,600 for the various outcomes. So this dice is fairly fair, right? So now I want to change it to another kind of dice that is not fair, that is weighted. So some of the outcomes should be more likely than other outcomes. And we need to be that ability, we need to be able to weigh things based on the probabilities later on in the course when we do the roulette wheel selection. So I can, of course, you can run this multiple times, you get a different output. But always 1,666 should be the correct value if I run this for infinite number of trials. So now I want to do a different type of dice. So I want a dice where I roll a 1 with 10% probability, a 2 with 20% probability, a 3 with 5% probability, a 4 with 20% probability, a 5 with 30% probability, and a 6 with 0.15% probability. So think about how you would model that. How would you change it so that you can now simulate rolling a not fair dice? And you should try and implement that yourself in Python. So don't look at my solution just yet. Try and figure this out on your own. And share your screen so that I can have a look at it. I'll just turn that into... And actually, I guess as you can see, it's not actually quite correct to draw it out of convenience. You can just use AXplot in order to plot a line, but this kind of event you should really plot as a bar chart, right? Because there's no value here for 2.5. There's no probability of rolling 2.5. And just in case you're not familiar with that, you can actually just use bar in Matplotlib to generate a bar chart, and that would be more appropriate for this type of domain. And this way looks a little bit better. I mean, I added the labels to it. So implement only one student sharing their screen so far. Make sure that you share your screen so that I can see what you're doing and how you want to simulate a non-fair dice. Append, not push back. So about the other students, 56H, 22H, 40H, 4H, Alan Tran, Carolina, share your screens. Sun, Marceline, Lo Chen, Kaiwen Dron, J6.
But I'm playing it alone.
Okay. And of course, your procedure should also work for a fair dice. Like you should be able to simulate any kind of dice. Okay, yeah. Using a accumulator is nice. That's a good good way for Ho Ji Lun. That's a correct approach, yes. Nicely done. Okay, we moved on from the hockey sticks. So if your screen still shows the hockey sticks, then you can start a new one. Nippy int. You have to cast it to an int if you want to use it in a range statement. So replace your rint with an int, int, that will be correct then. No np. Okay, we're rolling a whole lot of dice now. So then you want to plot this too to make sure, just like I said before, plotting just now I roll 1, then I roll 2, then I roll 3, then I roll 6, then I roll 1 is not going to allow you to figure out whether your probabilities are correct. So here's my approach at solving that problem of rolling an unfair dice with different probabilities. If I now want to make this one, let's say 0.15 and this one 0.35, then here I specify the individual weights. So first thing I do is I take the dice and I only care about the probabilities. Now this part here is list comprehension. It's one of the functional programming features that is included in the Python programming language. Dice has two components, right? The string with the name of the event and the probability of that particular event occurring. But for the rest of the computation, I need to know just the probabilities. So the standard way of doing that would be to write something like get piece from the list. or for event in list. Name P is equal to the event, and then result.append. Since I only want the probabilities, I append P, and then here I return it. That would work, but it's 1, 2, 3, 4, 5 lines. It's quite a bit of code for doing something fairly simple, and in fact you can do exactly that thing, the equivalent of it, in a single line. So for list comprehension, you usually have a for loop over either a range, so for I in range length dice, or for event in dice, or for SP in dice. Now, the whole procedure for list comprehension has to fit on a single line. In this case, that's pretty easy because for SP gives me the string and the probability, and then what I want out of that is just P. And then I put that in brackets, square brackets, in order to make it a list comprehension. So now the P's are simply the probabilities for the various events. And then I sum that up. Sum is a function built into Python which simply sums up all the elements in a list or an array. So that adds all of them together. Because I want to scale them, I have to make sure that there's at least some probability. So I have to make sure that this is not 0, otherwise I may be dividing by 0 here. So this line scales all the probabilities so that they're guaranteed to add up to 1 now. Right? Because if I write 0.72 here, then if I add them all up together, they'll be larger than 2, larger than 1. So I normalize them to 1 here. Yes. Oh. Wrong. So far, so good. So now I can think of these probabilities as weights, and I now calculate the cumulative sum from the left, and then I use random.random to get a random number between 0 and 1, and then I simply check which one is larger than the boundary. Then that would be the index. This is what I return here with my index. So in this case, 0.1, 0.2, 0.05. If we just look at the first ones here, then I generate a random number, 0.3. And what I want to do is that for the line from 0 to 1, 10% of the width I want to give to roll 1, and 20% of that width I want to give to roll 2, and 0.05, 5% of the width I want to give to roll 3. So what I can do is I can just generate a random number and then see which bucket, roll 1, roll 2, roll 3, up to roll 6, it actually falls into, which means I need to add up all the probabilities, the cumulative sum of those probabilities, and then I check. And the only tricky part then is I need to pick one. The last one will be 1, right? But that's not actually going to be tested. So I have to make sure that if I'm already in the last bucket, then this is the event that I will return. So this is the procedure for simulating non-fair dice or any other kind of event that has variable probabilities. So here's my dice, and I want to roll it, and I also want to plot it as a bar chart. Sample, where is the sample? Okay, here's the test. So this procedure is also called the roulette wheel selection, by the way. So here we have it, and you can see rolling a 2 is 20% probability, rolling a 5 is almost 0.4, rolling a 6 is 0.2, rolling a 3 0.3. So this matches the probabilities that I wanted to use for my dice here. Was 0.1, 0.2, 0.05, 0.15, 0.35, and 0.15. And this matches that. And then I can generate a dice factory so that I don't have to type them in as a list all the time. So I can now have a dice, of course, that rolls up to 20. If you play certain Dungeons and Dragons games, then you need a 20-sided dice. So I can now use my computer to model the probability of the different dice up to whatever I want to do with that. So I have 10 sides, I roll it 6 times and try it 10,000 times. Generate a 10-sided dice, and it shows the probability of rolling the different events that I want for my dice. So number of rounds. And then let's also set the label. Three. Okay. So let's make that a slide. And let's make it its own slide. then that's it for today. Exactly 12 o'clock. Good. So we'll continue next week with the central limit theory. Good. Okay, good. Then that's it for the class